Hope you guys are doing well. So today we will be continuing our journey in computer networks. So today we will be starting with the first, or I would say rather the last layer, that is the physical layer. So if you see in the OSI model, on the central side, this is the layer at which the actual connection, I mean the physical. Okay, wait. Yeah, so this is the one basically over which the bits will be transmitted over the medium. And uh, so here is how, like, this is the actual physical wire. And let's see, uh, so on the center, so this is the first layer, this is the last layer on the sender side. On the receiver layer, this is going to be the first layer on which the data packet is going to arrive. Okay, so physical layer. Okay, so here physical layer. Let's, so is chapter 2. We start the discussion of internet model with this layer, and then we have, okay, let's down. Okay, we start the discussion on them, but the bottommost layer, the physical layer, it's the actual layer that interacts with the transmission medium, the physical part of the network that connects network components together. Now this layer is involved in physically carrying information from one node to the another. It has complex tasks. First is to provide service for the data link layer. So in this layer, you would be having electrical signals, right? So on the receiver side, the layer above to it is the data link. So data link will only understand zeros and ones. So we need to convert our signal back into 0 and 1. The physical layer will also take care of physical network transmission medium, and then so there is no internal programmer logic. It is just the transmission. Okay, not signals. Another major function of the physical layer is to move data in the form of electromagnetic signals across a transmission medium. This transmission medium can be anything. Whether you're collecting numerical statistics from one another computer, sending animated pictures from a design station, or causing a bell to ring at a distance control center, you're working with transmission of data. Generally, so you're saying basically, uh, even though it may appear that we are doing something else, but it is basically all related to data and then signals. So analog signal, the analog and digital signal, the data can be either analog or digital. Analog refers to the information that is continuous. Digital is something discrete packets. For example, analog has a clock, minute, seconds. A digital will only have reports hours and minutes. It will change from 85 to 86. It will be discrete. Oh, okay. So for example, on the number line you have 1 to 10, right? So discrete values are basically 1, 2, 3. These are discrete values. So digital can take only discrete values. Data stored in the computer in the memory is in the form of zeros and ones. Can be converted to a digital signal or modulated into an analog for transmission across a medium. Now, analog and digital signals, like data, they represent signals, can be either analog or digital. An analog signal has many levels of intensity. As the wave moves from point A to point B, it includes a finite number of values along its path. A digital signal can have a limited number of defined values. Although each value can be a number, it is often as simple as 1 and 0. The simplest way to show signals is by plotting a graph. So this is a digital signal, this is the analog signal. So like these are different, like these are not discrete values. This is a discrete value. Periodic and non-periodic. So periodic signal, there are two types of analog and digital, periodic and non-periodic. So it's a periodic basically, which is the same as No, it's the same. Both of them are same. Now a periodic signal is something that will repeat over and over again. For example, the periodic analog. So if you consider this time, what does it let me? If you consider it, no. So this is so from year to year. You see, it's going to repeat again. So then we say that this is a this is sine wave is periodic signal. Now there is a method in signals and systems using which you can check whether the signal is it should be an even or odd multiple of 2 pi, something like that. I'm not so sure, but then it is. The peak amplitude is basically this much. The absolute amplitude in the negative direction. We only take the magnitude, not the sign. A power in a house can be represented as sine. So we have 155 to 170 watts. Again, it's electrical. It's common knowledge that the voltage of is this is basically AC to DC or however it's powered. And this is peak amplitude. So yeah, there are two. One is root mean square, and then one is mean square. So this is he's saying this has a high peak amplitude. This has a so root mean square is it will be under root of some b max square something. The period and frequency. So frequency is 1 by time period, and time period is inverse of frequency. Now two signals with the same amplitude on same phase. Now what he's saying is so the period is between one entire cycle is one period, and frequency is exactly inverse of that. So from year to year it's taking 1 by 12 seconds. In frequency it will be 6 something, inverse of this. Okay, the period is formally expressed in seconds, frequency is formally expressed in hertz, which is cycle per second. Oh yeah, this is seconds, right? So if you do an inverse it will be cycle per seconds. That's okay. Now 1 second in hertz is 1 hertz. Millisecond is so so these are basically units of how much is a millisecond, microsecond, and nano and pico. 9 hertz is 1. This is kilo. Mega is 6. Giga is 9. Tera is 12. Okay. The power we use at home has a frequency of 60 hertz. So it's 1 by what is the time period? It means that the period of the power is. So what he's trying to say is uh, our eyes have that means okay, this is something is this is very good what he has explained over it. So he's saying if you have an iPhone you can capture the flickering of the bulb. That means the pulses are coming in after every 16.6 millisecond, but it's so fast as eyes. But if you can you can use an iPhone to, let me check if there is an let me check if his iPhone capturing electric. This should be an using camera. If you point it, it shows. This is something else. Capturing an electric pulse. Is that? No, this is an oscilloscope. By pointing it towards transmission. If you point your camera, you can see the pulses. I don't know. Let's see. Electric pulsing. image real life. Sometimes you can see those pulses. Yeah, see. So this is basically what he's showing is these are pulses going around. This is a good image. So this is basically electric pulses going on. Similarly, our bulb will, so the frequency is how much? 60 hertz. It's just going to be, so every 16.6 seconds the light will flicker. Milliseconds, not seconds, sorry. How much can our eyes capture? Human eye capture rate is very less. Human eyes capture, how much? So we can 30 to 60 frames fps to millisecond is how much? No. It's okay. So how many fps is 0.16.6 millisecond? Does it? Okay, so 16 fps means a budget of 16.6 milliseconds per frame. And how much can human capture? Humans does like 30 to 40 something. Between 30 and 60. Between 30 and 60 fps. So if you make it more, then even if you do it very fast, sometimes you cannot see the cursor. So yeah. Expresses a period of time, so 1 by time period, okay. We already know the frequency is a relationship of signal to time, that frequency of a wave. Number of cycles is but another wave frequency is a measurement of rate of change. Automatic signals are oscillating forms. They continuously predictably above and below mean energy. A 40 Hz signal has one half frequency of an 80 Hz signal. It completes one cycle in twice the time. That's correct. Now to extend, what if the signal does not change at? What if it remains at the constant voltage level entire time it is active? Such a case of frequency is zero. Concept is, this idea is simple. If the signal, so what is saying? If the value of a signal changes over a period of time, the frequency is high. If the signal value is going very fast, the frequency is very high. If it is taking long time, then we say the frequency is low. What he's trying to say is, what does mean by frequency? Because and I don't know if that is working right now. This is a whiteboard, right? Save. No. Control Z. Pencil. Have this. No. Press shift. So then. So then now if you want to say frequency, alright, select color. Okay, so from here to here, this version is my F. Okay, now the greater this distance, lesser the frequency. So suppose we have one more control Z. So this is a very short frequency wave. If you see, it's alternating very fast. So then we say condenser, compute, pencil. Now this is short, right? So then we say this frequency is high because its time period is low, and this we say this time period is high. So inverse relation. I mean, before further going on, we should understand why are we so, I mean, why are we so worried about having this, and like, what's the point of studying? So if we see, this is our say, this is computer. I just gotta change the color. So this is computer 1. Yes. Oh no, I have it in this window. I need to this is computer 1, right? And then this is another computer. I assume this is a person who is in, so I say person in USA, and then he's trying to talk to a person who is in, say, in Canada. So you want someone, this is say, this is text, right? This say computer 2, and then this is another text, right? Let's move this down, or the text was a bit down. So this is person in, for communication to happen, these both guys needs to be connected, right? So then this is going to connect. So this is a wire, right? And this is a physical wire that is going to connect. Now right now we are talking about this connection, like so if this distance is far, then the signal intensity will reduce. So, but we don't want information loss away, right? But if the signal intensity reduces, information is lost. We don't want that. So then we will be performing some, we need to do some analysis of the signal. So we need to analysis. You may say, sir, optical fiber does not have any loss. Yeah, that is something else to debate right now. Now, right now we are not assuming, we are assuming that this is a very lossy medium. So these days you have, this is electrical signal, right? Remember. So this is so you are sending electrical signal. This has nothing to do with this is all electrical. This right now we have still not sent, like, this is a non-fiber medium. Always remember, like, right now we are assuming it's a non-fiber medium. these days you have fiber, right? So as the signals propagate, it will reduce its strength because it's a non-fiber medium. So we need to do some analysis. So we are studying about, and remember, in this medium, signal inside this will be electrical, right? But remember, both of these computers, that is this and this, both, they will understand only electrical. They understand only only zeros and ones. So they understand only zeros and ones. So at this point, there should be some conversion. So the moment we are here, some mechanism to convert that electrical to digital. We need a mechanism to convert electrical to digital, right? Same. No, here this is the sender. Let's assume this is my sender. Let's have sender. This is, let's see. Now at this point, from computer inform. No, he needs to perform some. So at this point, he needs to convert digital into electrical. So he needs some mechanism. So we'll study like which is the best one and why to use that mechanism. Yeah. So basically we are studying, and then we are studying about this transition the signals are going through. Yeah. What if a signal does not change at all? It maintains a constant one. So yeah, I told you about period. If the signal does not change at all, its frequency is 0. So phase is, now this is something phase. I don't know whether you need to study phase or not, but it's okay. Now wavelength. Okay. Now how much should be my wavelength? Now, wavelength is another characteristics of a signal. Now we are in the medium. Through a transmission medium, wavelength binds the period of frequency of a simple wave to a propagation speed of the medium. So what does wavelength tell us? The frequency is independent of the medium. The wavelength depends on both frequency and medium. Wavelength is a property of any type of signal. In data communication, we often use wavelength to describe transmission of light in optical fiber. So wavelength can be calculated is given by propagation speed of light. Basically this is the same formula like distance is speed upon time. I don't know, speed is distance upon time. So, yeah, so what is the wavelength? So the thing that we need to study is what should be. Okay, now there is, this is basic, and can skip this, and I will not, because this, now we are with this medium, right? So we know. No, this is not good. Let's erase this. So we say, speed times time is distance. Right, this is the formula, right? Alright, so does it go here? Speed times time is the distance. So we know the speed of the signal, we know how much time it is going to come here. So then we can guess the wavelength. What's the wavelength? So what is the relation between wavelength? So there is different media have different wavelengths, right? Medium wavelengths, not optical fiber. Yes. Okay, so this is basically a convention where we say uh, if the wavelength is this much, then it is. So I mean, what does wavelength indicate though? Let's have a new prompt. What does where what does it indicate? I mean, why do we need to know where wavelength in communication? Like, what does it give us? So basically, this is trying to say how much distance the wave can travel with a speed and a period. Is it? Let's say without going any error, without having any error, how much does it can travel? I don't know, but it. Although error correction will sudden wavelength of white. No. So coaxial cable has something called as velocity factor, I guess. So depending upon what the medium is corresponding. When I say wavelength, do I mean The propagation speed of an electromagnetic signal depends upon the medium, yeah, and the frequency. For example, in a vacuum, its speed is 3 into 10. The speed is lower in air and even lower in cables. The way we usually measure in microns instead of meters, the time and frequency domain. A sine wave is comprehensively defined by its amplitude, its frequency, and space we can be showing. So we have, and there are three distinct characteristics, right? This has a, okay. Domain. Now this is basically a amplitude time. We are still in time plot. Frequency domain plot is concerned only with the peak value. So this is peak value. So this is frequency. Or you just tell what the peak value is. Okay. Now it kind of the frequency domain is, so this the peak value is how much? It's 10, right? So no, it's not exactly 10, nearby 10. So the composite, so far we are focused on simple sine waves. Simple sine waves may carry many applications. For example, electric energy. There are two types, right? DC, AC. What is what we like? Why to use DC? Why to use AC? If you had only one single sine to conversion of the phone, it would make no sense. No, okay. To distribute electric energy to house and business is another example making the single sine wave is an alarm. First case sine wave is carrying energy. Second wave is a signal of danger. If you had only one sine wave to convey conversion of a phone, you will just turn up as we will see. So what he's saying is we don't send sine signals, we send a number of signals. Analysis. So simple sine waves. Now there is something called as Fourier analysis. We don't study. So instead of having exactly sine waves, we don't have sine waves. We do a composite signal. This can be both periodic and non-periodic. So then this is time. The Fourier transform basically does that. The time domain to frequency domain. Yeah, it's mathematical. No, bandwidth. Now this is something important. The range of frequencies contained in the sample signal is bandwidth. The bandwidth is normally the difference between two numbers. Now what is a bandwidth? Tell me. No, bandwidth. This is something important. The frequency cover. Okay, this is okay. Now see we check. These people always call and tell. Do you have the required bandwidth? Why is this something so talked about? This is every time when even if you have some issue with internet, you say, "Is my bandwidth good? Am I having the correct bandwidth?" Why? Why do we talk about bandwidth? Okay. Now composite. So what he's trying to say is, here you won't see an exactly sine wave. It will be sine wave with added features. Okay, and then he's saying, okay, so this is basically the repetition, right? After what time it's going to, so say f 3f, it should be an nf integer multiple, right? Now we don't know non-periodic signals. Okay, just give me a minute. So as you are saying, this is the most controversial thing that we would talk about. Bandwidth. What is this bandwidth? So let's see what is bandwidth. The bandwidth is refers to the range of frequencies over which a signal or system can effectively. Okay, so basically saying, oh, so remember, this. Now we are only considering. Um, so this is range of bandwidth which can be transmitted. So let's see, different mediums, below effective transmission. Let's see a coaxial cable bandwidth. So that means what is the bandwidth? What? So there are two things. Forget about fiber optic right now. So we have different types, right? We have restored pair, 1K to 1 gigahertz for shorter distance. So over this you can use, they would work. That's what he's trying to say. Oh, this is nice. Oh, this is a YouTube video. If you see this, the speed. No, he hasn't talked about bandwidth. No, is it converted? So that means if the signal that is over this thing, it will go effective. Okay, so what he's saying is, if the okay, let's have another page. Let's go to page. So the first term that we are trying to understand is there will be this. Let's have a text bandwidth. So basically, it kind of tells what frequency range and what distance will it be transmitted without any error or something. Yeah, what frequency range should be the signal in, and what should be the distance. I guess it says that. So if you go, no, go here, text, and then go on this. Does it move down? So this indicates the distance and the frequency, the signals, which would not. It indicates the distance which will go. So it indicates like what is the acceptable latency and the distance of the synthesis bandwidth. Okay, now, so that means the modem should convert it into a desired bandwidth. The modem converts the latency into a signal of a specific bandwidth. The modem demodulator. Oh. Okay. So the modem should also know the bandwidth. It should know, right? Must match the bandwidth of communication channel designed to operate on. So he's saying, so he's saying, why do we need a, I see. So now remember, in our network, so now let's see, this is our home network. Let's get this thing to some color. This is our home network. Now you have something. Does it draw shapes or something? Oh yeah, good. So let's get this something. It's a right angle. Now, oh no, this is gonna be something purple. And then now you have a wire coming in. This is coming from the ISP or service provider. This is the service provider, and then this is our local area. So if you say let's you know what, then have a text. It's a local area network. Okay. And then so let's have this connection. And then what else we can do is but local area is basically our devices. We have phone, computer, TV, whatever. So now this wire will have a specific bandwidth. Okay. So this is our modem, right? Why it's a modem, we'll see that in some other. It is a demodulator. So this short form is modem. This is modem. Full form is modulator demodulator. Short form it is called that way. Yeah. Let's make this. Does it move? Oh yeah. Okay. So now this model will do the conversion to digital over here. So if I say over here, at this point, modem does digital to analog. So now what frequency the modem should know the acceptable frequency of the coaxial cable while it does the modulation and demodulation. If this is something out of, if the bandwidth does not match, it's as simple as that. Those going to those signals. If bandwidth does not meet, signals will not be transmitted in an efficient way. That's the whole gist. Yeah, that's weird. Okay. Now how to calculate the bandwidth? So there are two ranges, right? The upper and the lower. So how you calculate it? Basically. Now digital signals. Now, in addition to being represented by analog signal, information can also be represented by a digital signal. For example, I can encode a positive voltage and zero. A digital can have more than two levels. So you can have 0 and 0, 0, 0. So positive indicates this. Now inside one bit, okay, now there is something. What he's trying to say is, in addition to being represented by analog signals, information can also be represented by a digital signal. For example, I can be encoded a positive voltage and a zero as a negative zero voltage. Digital signal can have within two levels. So basically, you're saying these are two levels. One is here and then. So how many levels? That is that number of bits. A single signal has 8 levels. How many bits? Well, so the more the number of levels, like more these bits. So what he's saying is, I mean, this will be more clear when we try to truncate signals from analog to digital, because there is where the problem is. What if I only have one level over here? Information in between these levels will get truncated. We don't want truncation. So then we have more number of levels. So then bit rate. So how many bits per second am I? Now what is this bit rate? So if you see this is okay. Then let's have a new page. Oh, it's only two page. We can have one more. Let's get rid of this. So now here, what this is? Oh, this is go and add a page. Let's draw something. So the signals will be digital analog, right? Let's come. Let's this is good. And let's have One more. Oh, no. Let's see. This is one more. Why does it happen this way? 7, 9. Okay. So then this is yeah, and then so this will have different levels, right? This will have different levels. So these are different energy levels. So this is now. So what if we say that this level is corresponding to say 5 and here 5 volt is this much. You say this is my 5 volt. So then what is going to happen is this is all going to get truncated from here. So anything that touches this will be my will be the logic one. So you just go and draw. This is 5 volt, right? I mean, actually that shouldn't be, it should be placed a little bit up. And this, oh yeah, I can move this thing. Right. Let's say this is 5 volt, right? So this level is my 5 volt. So this portion will get truncated. So if I have more levels, this is only one level. I have say one more level over here. So then I can capturing more information. Okay. Okay. Now bitrate. Bitrate is most digital signals are non-periodic and thus period and frequency are not appropriate characteristics. Another term bitrate instead of frequency is used to describe. Bitrate is the number of bits sent in one's expression bits per second. What is bitrate? How we do bitrate? Even this is measured in bits per second. Bitrate. Bit refers to the amount of data transmitted per second in the communication systems, typically measured in bits per second, indicates the speed or capacity of a transmission. Bit rate is a key metric in digital communication. Now, what does this bit rate indicate? Amount of data transmitted per second. Now I is number of data per second in a communication system measured in bits per second. You need to scroll up. Just bit rate. Most signals are non-periodic, thus period and frequency are not appropriate characteristics. Another term bit rate is used to describe digital signals. The bit rate number of bits sent in 1 second expressed in bits per second. Bitrate is the number of bits sent in 1 second. Mm. Assume we need to download text documents at the rate of 100 pages per minute. I mean, what is the goal of number of bits? What does it? Oh, so it is. So the thing is, bits rate. Rate is basically something that is in measured respect to time. And then if I say it in bits per second, so I'm saying one. Okay, I guess so. 10 power 3 bits are getting transmitted per second. Oh. Now there is a relation between bits rate and bandwidth. So factors affecting bit rate. That means oh. Now is a larger bandwidth allowing for higher bit rate. Larger bandwidth means I have larger number of signals that can be transmitted. Okay. So let's see. I see. Larger bandwidth means wide range of signals can be transmitted, and so at the modem end that many uh, now how is he relating bandwidth and bit rates? A larger bandwidth allows for higher bit. So there is a relation of bandwidth and bits bit rate. He's saying if I'm giving kilobits per second, so I say kbps. This is correct, right? Wide range of frequencies. Okay. More amount. So because signal will be converted to analog, and wider bandwidth means wider range of signals capturing more information. Is that what he's trying to say? Okay, that's okay. But then now how is now is he saying bitrate and that conversion? So now we are trying to understand the relation of bit rate and um, bit rate and bandwidth. Like why is higher bandwidth and high bit rate, how they are related to each other. Higher bit rate. Now is high bit rate larger number of bits per second. But then how does bit rate link to bandwidth? Oh, okay. So this is something interesting. I don't know if you have Mac or by higher bit rate is I have more number of bits in 1 second. But how is bit rate converted to analog? I mean, how's that thing? I say high bit rate means mm, amount of data that can be transmitted per second over channel. Mm. Mm, bitrate and bandwidth are closely related but related to different aspects of communication. The bitrate, amount of data that can be transmitted per second over the channel. Hmm. Higher bandwidth, how is a higher bandwidth allowing higher bitrate and higher bandwidth related to each other? How are these two? So higher bitrate are closely related, they are not the same thing. Okay. Okay, this is also is you know what he's saying is, since more frequencies can be put on a bigger bandwidth, so more data is being sent. Something like that he's trying to say, I guess. Leading to higher bitrate. Yeah. Okay. Now digital signals as a composite signals. Okay. Transmission of digital signals. To previous discussion. Okay, baseband transcending a digital signal or channel without changing. Now there is something called as baseband transmission in which you directly transmit digital. But generally, do we use baseband? The problem is baseband is there is an issue. But he's saying, can we do direct? Oh, so most common example is saying is LAN. Other thing, internet has baseband. I see some. In baseband transmission, do we directly send digital? Without modulation or into, there is no modulation. So does LAN do baseband? So you're saying local area networks, Ethernet. So that means, oh, so an Ethernet cable needs digital signal. Yes. But how? Let's see how Ethernet. Let's see how an Ethernet cable looks like. The Ethernet cable. Let's dissect it. Internal. This is a twisted pair, right? Yeah, this twisted pairs. But it's but how does it recognize? How does Ethernet cable recognize 1 and 0? Not But then in baseband we directly send digital. Indirectly it's going to get converted to electrical, but then baseband does not. Yeah. Okay. Okay, so I interpreted it as wrong. Baseband is the digital signal to analog. Ethernet to Ethernet. You directly go. Also, the bandwidth of this channel is 0. Low pass and high pass. Low pass. Example of a dedicated channel. Okay. I see. But on the wire it is going to be electrical, right? But there is no modulation. We are not doing any modulation or something. That's what it's trying to say. Modulation of a digital signal for a transmission on a band pass. So input digital signal, you have an output digital signal, you have another A to D, D to A. So he's saying in Ethernet there is no Ethernet cable perform conversion like digital to analog. This is perfectly category. Then how does it transmit it? And how? Oh. So what is the difference? Of using a modulator demodule? Like what's the advantage? but then even in Ethernet we send electrical drive. So where does the conversion happen? Ethernet uses directly in baseband mode. That means there is uh, 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 so you do like a something called as okay. The NIC handles it. You don't need a signal. I see. So Ethernet cables do not do electrical. The transmission and air impairment, like when we say, so there can be attenuation, distortion, or noise. Attenuation is basically loss of energy. For example, null conservation of energy, right? So let's go page 4. Now there are impairments like problems. This is what this is more where we analyze impairments. So one is basically now what are the causes we say? Okay, you kind of have multiple things. So then first is okay, let's have a text this now. Attenuation. This is reduction in signal strength. Let this A, and then now let's have. No, it doesn't do that. Signal strength decrease. This is basically law of energy conversion, right? Law of conservation. Then next thing is distortion. Distortion is like shape change. I guess attenuation is loss of energy. Noise is basically we not talked about distortion. Noise is because noise and distortion are kind of the same. So once they travel, they have this electromagnetic thing, right? Distortion means shape change. Yeah, distortion is basically change of shape. Okay. So if I say shape change distortion, then I say noise. So noise is something any unwanted uh, unwanted signal. We don't want this. Since this there is now we checked about environment about problems right now. There should be a measure to check the performance as well, right? So then we have something. We have 2 to 3 terms. Okay, let's check each of them. Okay, the first thing that we have is bandwidth. As I said, greater bandwidth means more number of frequencies it can travel. The more frequencies is when we do so latency. Okay, bandwidth is already discussed. So then this throughput. Uh, so how fast we can actually send data through a network. That means sender to receiver. That time is throughput. And then latency. Okay, so there is bandwidth is I said. If I have a high bandwidth means a digital signal converted by the modular to an analog can capture more bits. Is it something? Is high bandwidth means more signal, high bitrate, more bits are transmitted, and is it something? Because this data is ultimately converted to electrical, right? That's what he's trying to say. So more the pulses have more information. More electrical pulse, more information. Okay. Okay, throughput is single time. So okay, now let's move on to writing something. Bandwidth. Okay, let's add some terms here. So I say bandwidth means bandwidth. So then means more frequency of signal range. Okay, and then let's say bit, we have bit rate, right? Bit rate is number of bits sent out. Number of bits being transmitted. Now how these two are related is rate of bandwidth means more signals, which eventually means more bits. Now then we have something throughput. Throughput is one side time from sender to receiver. This is throughput. And then let's make this into pink. Then there is one more, right? Round trip time or latency. So latency is time taken for message to completely deliver. So you see latency. And then you time taken for message to completely deliver or basic number time before sending the acknowledgement. The acknowledgement. Now what else? Queuing times. Okay, now this is how the request is queued, right? You'll wait. Jitter. Okay, this is hasn't talked about how digital. So this is basically this digital transmission means how efficiently is the digital to analog and analog to digital. So there are different types of bipolar. But this is not This is not needed for our car information right now. This is more towards digital signal, TDM, FDM. This is not error, how to calculate error, unipolar, bipolar. No. So this is how digital mode. You can have a comp sampling, quantization, and encoding. Then you determine something called as Nyquist rate. How many samples can we take? That is determined by Nyquist rate. Not needed as such here. No. This is not needed. Not needed. This is just a good thing to remember, although not needed here. This has nothing to do with computer networks. It's more sort of signal analysis. This again. So then you have a modulator, demodulator. There are so many ASK. This is actually electronics engineering syllabus, not for our computer networks. This much is enough. No, this is not. Oh, there's something called as eavesdropping. We'll see later on. Eavesdropping. I did say something like eavesdropping, no? This is nothing. Okay. So this is how a coaxial looks like. Now what is that resistance? Again, this is of no use. Okay. These are basically connectors. Oh, this is something. In the fiber optic, you will have. This is the glass thing. Then. So this is ionosphere. No. This is again different. No. This is for mobile communication. Yeah. How an antenna is determined. No. Next thing should be data link switching. This is, we haven't yet studied about IP networks. What is IP? What is port? Doesn't make sense to have switches right now. Yeah, this is, we have already done this. Yeah, this is something important. DSL and ADSL, we'll see that. So then, yeah, the thing is, what I wanted to search is bandwidth is always fixed by the medium. Uh, Speed can Mbps. There's no issue with the bandwidth as such. So when we say slow speed, it is not a bandwidth issue, as it will be as bandwidth is fixed, medium dependent. Yeah, so slow bit is not. This is, and this is. I can add one more point is this is medium related, which is fixed. Where did the page go? Yeah, this is okay. That is all for this lecture. In the next one, we'll study about DSL and CMTS, but network, but how ISPs provide network to frame it more accurately. That's all for this lecture. Hope you guys have a good one. Take care. Bye bye.